Hello everyone, welcome to Artistic Atom channel. I'm Fatima and in this session we will learn an easy trick to crack electrophilic substitution reactions in a benzene ring like a pro. We will understand activating and deactivating groups, ortho, para and meta directing effects and the logic behind these reactions in a very simple and interesting way. So grab your notes and let's get started. So before going and understanding the exact trick, let us first understand what is the overall idea behind this trick. So in this trick, we will be using electron donating groups and electron withdrawing groups in order to determine the exact positions where the substituted product or the group will go and attach itself. So before going deeper into the electron donating and withdrawing group concept, let us first understand how they will help us in determining the exact product. Well, when you have an electron donating group attached to the benzene ring, it usually donates its electron to the benzene ring and activates it so that it can undergo electrophilic substitution reaction easily and results in the increase in the electron density at ortho and para position, due to which it results in the formation of ortho-para directed products. Now, when you have an electron withdrawing group attached to the benzene ring, it withdraws the electron from the benzene ring, due to which the electron density of the benzene ring reduces and hence it deactivates the benzene ring as a result. Now, when it is deactivating the benzene ring, so if we compare all three positions, that is ortho, para, and meta, compared to ortho and para, meta will have the more electron density, due to which the possibility of the substitution as at this particular position is higher compared to other two. Hence, it will result in meta directed product. So this is how we are going to use these two groups in order to predict the product. Now, when we talk about electron donating group and electron withdrawing group, we should understand how to make out which group is electron donating and which group is electron withdrawing. So for that, here we have easy points that we can remember and use these points so that we can solve these questions. So when you have lone pair of electrons given on the group, that particular group will donate its lone pair of electrons to the benzene ring and result in the activation of that particular ring for the substitution reaction. Hence, if you have lone pair, then you will call that particular group as what? Electron donating group. If you have double bond or triple bond attached to the oxygen atom or nitrogen atom, well, double bond is for the oxygen atom and triple bond is for the nitrogen atom. Nitrogen can also show presence of double bond, okay, in nitro group. So in that case, it will act as what? Electron withdrawing group, because the electronegativity of these groups increases when they are attached to the pi bond system and results in withdrawal of the electrons from the benzene ring, causing the benzene ring to deactivate itself, and hence it will result in what? Meta directed products. Now, when we talk about alkyl groups, so since alkyl groups, they have less electronegativity compared to the carbon atoms of the benzene ring, they act as what? Donors. Hence, they will called as what? Electron donating groups. Now let us understand each one of this in detail. So firstly, we will be discussing electron donating groups. So when we have electron donating groups, the characteristic feature is that they have lone pair of electrons. Since they have these lone pair of electrons, these lone pair of electrons can easily undergo resonance with the pi electrons of the benzene ring, to which we call it as what? Positive resonance effect or plus R effect. Now, this effect increases the stability of the benzene ring. At the same time, it increases the electron density. Now, this increase in the electron density is at the specific positions. So, in order to understand this in depth or in clarity, we will take an example. So, here, as you can see, here I have shown that here is the attachment of an electron donor, that is electron donating group. So, since they have those lone pair of electrons, these electrons can easily undergo resonance with the pi electrons of the benzene ring, as we have discussed. Now, these pi electrons, they undergo resonance and results in the increase in the electron density on the benzene ring. As you can see over here that this position, and this position in this whole mechanism has the highest electron density. Hence, these positions are the most favorable positions for the electrophile to come and attach, because electrophile is an electron deficient species. Hence, we will get what? Ortho and para directed products only when we have electron donating groups attached. Now, let us take a specific example. Here I have taken the example of phenol. So as you can see, phenol, in case of phenol, this particular OH group, in this oxygen atom has a lone pair of electrons. So these lone pair of electrons can easily undergo resonance with the pi electrons of the benzene ring. As you can see the whole mechanism over here, and it results in the increase in the electron density at ortho and para positions as we have discussed, and these positions then can easily attack on the electrophile and results in the substituted product. So since we have higher electron density at ortho and para only, it will result in the formation of what? Ortho para substituted product. This is how actually we are going to use this trick. So in conclusion, we can say that electron donating groups, they actually activates the ring and result in the formation of what? Ortho para directed products. Now, when we talk about alkyl groups, so let us understand how exactly alkyl groups donate the electron to the benzene ring. Now, when we talk about an alkyl group, we can take any example. Here I have taken example of what? Methyl. So here this methyl group is attached to the benzene ring, and this whole compound is called as what? Toluene. Now, in this particular compound, this carbon atom of alkyl group is sp3 hybridized, whereas this carbon atom of benzene ring is sp2 hybridized. And according to the concept that we have learned in our standards, previous standards, we know that the electronegativity of the sp2 hybridized carbon atom is more than that of the electronegativity of the sp3 hybridized carbon atom. Hence, this particular carbon will continuously pull the electron from this particular group. So we can say that this group is actually donating its electron density to the benzene ring. Hence, this group will also act as what? An electron donating group. So since this is also an electron donating group, it will result in the increase in the electron density at ortho and para position, and as a result we will get ortho para substituted products. So alkyl groups, they are also activating groups and results in the formation of what? Ortho para substituted products. Now, nextly, we have halogens. Now, this is a special case that we should understand, because in this case, what happens is there are two factors that we should consider. First is halogens, they have lone pair of electrons. Second is they are highly electronegative atoms in the periodic table. So this means due to their lone pair of electrons, they can easily donate those electrons for the resonance. Secondly, since they are highly electronegative, they can pull the electron density from the benzene ring through minus I effect. Now, how to decide the product in such case? So, well, in that case, we have to first understand inductive effect. So when we talk about minus I effect, so in that what happens, if we have an electronegative group attached, then in that case that particular group starts to pull the electron density from the other group. So here in this case we have benzene ring. So this chlorine is continuously pulling the electron density from the benzene ring. At the same time, we can see that these lone pair of chlorine, they can easily undergo resonance with this benzene ring. So if we compare the plus R effect and minus I effect, we can see that minus I is stronger than that of plus R effect. So since there is strong minus I effect, we can say that the benzene ring is slightly deactivated compared to the previous donating groups that we have seen. but at the same time, since there is slight more resonance, okay, so there is additional effect, electronic effect present, that is nothing but the resonance effect. So that resonant effect is slightly causing increase in the electron density at ortho and para position. Now if we compare this electron density to the previous examples that we have seen, the electron density is less, okay, but still it is there. So that's why these ortho and para positions, they are available for the electrophilic substitution reaction. So we can say that since the minus I effect is more than that of plus R effect, overall the halogens, they are electron withdrawing group, and they deactivate the ring. And at the same time, since there is a resonance effect plus R effect, which is less than minus I, but it is still there. So due to that effect, the electron density is still increasing slightly at ortho and para position. Hence, it will also give what? Ortho para directed products. And these are the examples that we have seen on the previous slides. So if we compare the reactivity of halo substituted benzene ring and these substituted benzene ring, then the reactivity of these groups will be higher than that of this. Why? Because the minus I effect is slightly decreasing the activity of this particular benzene ring. So this is how you're going to decide the exact position where the substitution is going to happen. Now let us understand electron withdrawing groups. So when we talk about electron withdrawing groups, so in that we should remember one important point. That is, if you have a benzene ring on which there is oxygen or nitrogen atom kind of groups attached with a double bond or a pi bond system, we can say in general. So at that point of time, the electrons from the benzene ring will be pulled by the groups attached. Now, due to that, what will happen? The electron density of the benzene ring decreases, and due to that, these groups, they deactivates the benzene ring. Now, let us first understand this, and then we will move forward with the substitution. That is, on which particular position these groups will substitute. Okay, so here I have taken an example of an electron withdrawing group. So as you can see, this particular group is there. It will pull the electron density from the benzene ring through minus R effect. Okay, so due to this minus R effect, we can clearly see that there is a positive charge at ortho and para position. What do you mean by this positive charge? Well, it is the indication of the electron deficiency. This means ortho and para position, they are electron deficient. But if we compare the meta position, we can see that the electron density is slightly higher than that of ortho and para position because there is no positive charge. So we can say that meta position is more favorable to undergo an electrophilic substitution reaction. So if we take an example, as you can see over here, I have nitrogen with a pi bond system. So in this case, what will happen? It will pull the electrons towards itself and results in the positive charge at ortho position. If we do the similar way for the para position, you can see that again we have a positive charge at ortho and para position. So if we compare all three positions, we can see that ortho and para, they are positively charged. This means they are more electron deficient than that of meta position. So meta position is the most favorable position in this case. Hence, in conclusion, we can say that electron withdrawing groups, they deactivates the ring and results in the formation of what? Meta substituted products. So in summary, this is what I have made. So using this, you can easily make out which groups are meta-directing, which groups are ortho-para-directing. Just remember the concept that we have learned just now. That is, if we have electron donating groups, they will result in the activation of the benzene ring and form what? Ortho-para-directed products. But if we have electron withdrawing group, they deactivate the benzene ring, due to which the electron density at ortho and para position decreases, but comparatively meta position will have slightly higher electron density. Hence, due to that, meta will be the substituted, meta will be the favorable position for the substitution. Now, if we talk about halogens, they have minus I and plus R effect, where minus I effect is higher or stronger than that of the plus R effect. So due to minus I effect, these groups they deactivates the benzene ring, but at the same time, due to slightly plus R effect, the electron density is higher at the position of ortho and para. So due to that, ortho para substituted product will be obtained. So this is how you're going to determine where exactly the group is going to attach on the benzene ring. So with this, we have completed our session. Thank you so much for watching. Do like, share and subscribe to Artistic Atom channel. If you have any query or any doubts, you can mention it in the comment section. If you want me to make a video on any specific topic, you can mention that too. Thank you so much. We will see you in the next session.